Welcome to the Research Cortex. And our first math snack. Our first view will give you a bite-sized overview of various types of proofs used in mathematics. Part 1 in this series is the most common type, the direct proof. Suppose we are given two statements, P and Q, and we want to show that if P is true, then Q is true. Typically, these are written in English as if P, then Q. So for an example, if it is raining outside, then I will spend the day in pajamas. Mathematically, we express this using the symbol P implies Q. Now we're going to need to construct this symbol in a way by building it through logical stepping stones that lead from P and end at Q. This is called proving the statement. Now let's take a mathematical example to illustrate how this works. If x and y are odd integers, then x plus y is an even integer. The first stepping stone we need is first principles, or definitions. I find it helpful to look at first principles on both ends, not just the starting end, in order to see what I have and where I'm going. First, I'm going to need to know what it means to be an odd integer. If x and y are odd integers, what does that mean? X is an odd integer if there exists an integer n such that x is equal to 2n plus 1. Quick example. Let's look at the number 3. Is 3 odd? Well, conventionally, we all know it is, but does it fit the definition? Well, 3 can be written as 2 times 1 plus 1. Therefore, there exists an integer n such that 3 may be written as 2 times that integer plus 1. Thus, 3 meets the definition of an odd integer. Similarly, we need to know what an even integer is. We're trying to show that something is an even integer, in this case, x plus y. But we need to know what it means to be even so we know where we're trying to go. An even integer is an integer such that it may be expressed as 2 times another integer. So 6 is equal to 2 times 3. 3 is an integer, and 6 may be expressed as 2 times that integer, thus 6 is an even integer. Now let us use these definitions to build our proof. It is important to note here that we must use generic x and y here. Examples do not constitute proof. Telling me that all the sums of odd integers that you can think of are even does not imply the statement is true. Therefore, we must create two unknown odd integers using the definitions from before. So x is odd, so that means that x can be written as 2 times some m plus 1. I don't know what x is, I don't know what m is. All I know is that this is what it means for x to be odd. It can be expressed in this way. Similarly, y is equal to 2 times n plus 1. I have created another odd integer y that is distinct from x, but may not be. It can be expressed as 2 times another integer n plus 1. Now we need to make sure we don't use the same letter, because otherwise then we assume that m is the same for both x and y. N and m may not be equal. So, that's what we've started. Now what are we trying to look at? We're trying to do something with x plus y. So let's look at it. The next natural step is to look at x plus y. So x plus y, using our representations from the definition of an odd integer, can be written in the following way. 2 times m plus 1 is x, and 2 times n plus 1 is y. So here I've changed nothing. I've simply written it in a slightly different way. Now I can manipulate this new representation, and let's see if we get something out that's interesting. Keep in mind that our end goal is to look for the definition of an even integer, because we're trying to show that x plus y is even. Now, let's write this a different way. So, we may write this as 2m plus 2n plus 2. Everything involved is an integer, and we may use conventional addition. I'm going to re-express this because we can see that there's a common 2 we can factor out. 2 times m plus n plus 1. Now this is starting to look awfully familiar. We looked at the definition of an even integer, and it looks awfully familiar. The only thing that we're not quite sure about at the moment is m plus n plus 1 an integer? Well, sure, if m was an integer, and n is an integer, and 1 is an integer, we already know that the sum of integers is still an integer. Therefore, what I'm going to do is I'm going to call this quantity, I'm going to call him w. So then I may express this final statement as 2 times w, where w is an integer. Now I don't know what w is because I don't know what m and n are, but I do know that w is an integer and that x plus y may be expressed as 2 times that integer. Therefore, x plus y fits the definition of an even integer, and since that was my goal, we have proven the statement. For our first snack, we looked at proven statements to be true directly, building the path from P to Q from first principles. Our next snack will be a look at what it means for two statements to be equivalent and converse statements. Thanks for watching Math Snacks, brought to you by the Research Cortex.